Hello, Stat. Hope you're doing well, and I hope I'm doing well. We're looking at Stat Day 7, so on those notes, let us begin. What we're talking about today is this idea. Experiments with completely random designs should have not only random assignments or treatments, but principles of control and replication. So we sort of ended on that note previously, where we talked about three important aspects of experimental design: randomization, control, and replication. So starting on that note, let's repeat that, and you can write that again. And again, as if you need more time, have someone stop the video and get that down before I go if I'm moving too quickly. So, some experiments are better when blocking is used. And blocking is what we're going to talk about pretty much this whole day. So let's see what blocking is and what benefits it adds to our experiments. We'll do that by looking at an example. It's always easier to learn things that way. So in this example, we have hand wash, and there are certain items that you're supposed to only hand wash. And we're looking at a hand wash detergent, and we're going to do experiments with a hand wash detergent. And the question is, does this detergent work better in hot water or cold water? So that's the basic question that we're going to design an experiment to answer the question. So it seems pretty straightforward what the experiment would look like. So one method, and this is what we've seen so far, would look like this. So you're going to take many pieces of dirty laundry, lovely, and you're going to do a random assignment between them. And part of them is going to go into the hot water, and the other half will go into the cold water. And then you will rate the cleanliness of the items at the end of the process on a scale of 1 to 10. So you can compare. So it looks like a pretty healthy experiment. We see randomization, we have many pieces for replication, and we have a comparative step. So it looks pretty healthy. However, in this case, sometimes, and in many cases, sometimes even before the experiment is conducted, we know this just from life experience, we know that there is another variable, a lurking variable, that will affect the outcome. Does anyone know what it might be up here? In the olden days, we learned about washing items, so I know what it is, but perhaps you do or perhaps you do not. So pause a minute to think, what might be a variable, a lurking variable that would affect the outcome when we compare these two groups? Well, the idea is this experiment should use what we call a block design, because it is a known fact that white or light colors, I'll call them white, but there could be light colors, wash better in hot water, and dark colors or bold colors wash better in cold water. Does everyone know that? Okay, that was a given when I was growing up. I still separate my laundry, but I don't think any of my kids do, so maybe it's a generational wisdom thing. Alright, so let's see now what I can do with a block design. So I'm going to redesign my experiment, and this is called blocking. After I explain the experiment now, we'll discuss what blocking actually is. So, such a glare in here at night. So, let's try that. Alright, so I'm going to redesign my experiment, and this up here was a randomized experiment. It had some merit, but since I know that certain items wash better than hot and others wash better in cold, I'm going to use a block design to actually prevent the variation from that known fact. So I'm going to take those many pieces of stinky laundry and I'm going to divide them into whites and darks. Whites and lights, darks and bolds. So I want to put a little note here because I want to say something about that later. So a little reminder star. After I divide them into whites and darks, I'm going to do a random assignment, first of the whites between cold and hot water, and then from the darks between cold and hot water, and I'm going to compare the results. So these blocks are an important form of control. They control the effect of some outside variable by bringing those variables into the experiment to form blocks. So this is one block. And this is one block. A randomized block design, that's what this is now called. A randomized block design allows us to draw separate conclusions about each block. For example, the light colored and the dark colored clothes in the laundry experiment. So blocking also allows precise overall conclusions because of these systematic differences between light and dark colored clothes. So these differences can be removed when we study the overall effect of using this detergent in warm and cold water. So here we're going to come out, and we might come out with a result such as, well, in the whites do better with this detergent in cold water, and the darks do better in cold water. So we're not sure. We only can block for what we expect. So we're not sure what the expectation, what the results will be. But because we know from many exposure to this situation that whites do better than hot and darks do better in cold. So then when we look at these we're going to compare the whites with the whites and the darks with the darks, so that we have removed the variable of color from this experiment. It's called blocking. So let's do a definition then of blocking. And first of all, note that blocking, let me cover up some of this. Blocking, there's my glare again. Sorry about that. Blocking is another form of control that can be added to experiments. And we will define blocking is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect the response to the treatments. So that's a lot of words. So let me write those down. The definition of what a block is. Having seen that example, these words are understandable. So a block is a group of experimental units in this case the white laundry and the dark laundry. So experimental units, we call them subjects when they're people, but definitely not this time. So a block is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect the response. Alright, so a block is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect the results. Okay, so response. So now we're going to be using, when this happens, we're going to use a randomized block design. And the random assignment of experimental units to treatment is carried out separately within each block. So that's where I want to go back to that little star that I did to remind me. So back we go. All right, back here, when I was drawing out this randomized block design, I just wanted you to make note, because this is sort of a point of question sometimes. So right here, when I began this experiment, or design of this experiment, I started with my many pieces of dirty laundry, and I divided them into whites and darks. Was this a randomized process right here? So no, this was not random. There was no random process right there, because either it was white or it was dark. So I didn't have to flip a coin to see which way it went. It was defined by its very nature. So this was not random at this step. This step right here, once I have the block of whites and the block of darks, then the randomization occurs. So by random, I assign some of the whites to cold and some to hot, and likewise with the darks. So that is an example of a randomized block design. Let's see what another example would look like. Let's say we have two brands of cookies that we're baking. Cookies A and cookies B, two recipes. All right, and we want to know which one is the best. So there's 10 of, sorry, the reading of this is so difficult. Can't get the lighting very good. Let me zoom in and see if that helps. All right, so we have cookie A and cookie B, and 10 of each are going to be baked on 2 trays. So fairly big cookies are only going to put 10 of each on two trays. So we'll have 20 cookies, 10 from recipe A and 10 from recipe B. So what should we block? What should we make a block for? Any ideas about that? Think about that. When you're baking cookies and you're going to have 2 trays, what could affect that? And we kind of know that just from life experience. What could affect that is whether the tray is on the top rack in the oven or the bottom rack. Have you ever noticed that they bake differently? The ones on the top, I think they actually bake faster on the top. I don't know. It may be browner on the bottom. I don't know, but I knew the answer for laundry, but my cookie skills are lacking, so you'll have to help me with that. I do know they cook differently, so let's block for that. So if the cookies bake differently on the top rack and the bottom rack, here would be a randomized design. Oopsie. Okay, back to Glareland here. Alright, there's 20 baking spots in the oven, so this is where we are not randomizing it. We're going to put 10 at the top rack and 10 on the bottom rack. And then, once we've decided that there are 10 spots on the top and 10 spots on the bottom, we are going to randomly assign recipe A 5 on the top, so this is my top rack, and 5 from recipe B. So on the top I have 5A and 5B, and then on the bottom I have random assignment 5A and 5B, and then I'm going to compare the tops to the tops and the bottoms to the bottoms and see which recipe comes out the best. Now it's possible that on the top A is better and on the bottom B is better, so then we can't make any clear conclusions of which is best of all. So, but that is the truth of the matter, and we have to consider the truth. So right here, this was not randomly decided. We are going to pick 10 baking spots for the top rack and 10 baking spots for the bottom. The randomness came when we decided what 5 cookies from A would be on the top and which 5 cookies from B would be on the top. And similarly on the bottom. So, the moral of the story is that when you're doing an experiment, you want to control what you can. So if I'm going to make an experiment, maybe testing aspirin. Does aspirin help with reduction of heart attacks? I want to make as much control in that experiment as possible. So I want to control everything about my participants except the fact that one group has aspirin and one doesn't. So I'm going to control whatever I can. And those things that I can control, I kind of do a block design so that the variations due to the blocking characteristic will not affect, the variation due to that blocking characteristic will be erased from the experiment. So I'm going to block what you can't control. So you control what you can, block what you can't, and randomize to create comparable groups. So that is my new direction for experimental design. Now we'll continue today and finish with the idea that there is a special kind of block design, and this is still block, but it is a special one. And this special block design uses 2 experimental units. So if there are people, there's only 2 people, and even that can be lowered. So I'll put a little, instead of putting a block around it, I'm going to put quotes around it. So why would I put a quote around 2? I'll explain that in a minute. There is a special kind of block design which uses 2 experimental units, 2 subjects, and 2 treatments. And that creates a block with 2 subjects that are similar to one another, and they randomly decide, we randomly decide which subject gets which treatment. And then we compare the results between the 2. And that has a name, it's called matched pairs. For some reason, our book and the AP test and everything, they just go nuts with matched pairs. They love matched pairs. Those questions will pop up in your statistics future. So a matched pair is a form of blocking when there's only 2 persons in the block that are similar to one another, and they will get 2 treatments. And I put this in quotes, and you'll see why in a second. So why do we do this kind of blocking? It reduces variation among the subjects. So if we are testing a product among a whole classroom of people, there's going to be so much variation in the people. But if we test between 2 people, we have limited natural variations that can occur. So matched pairs are often a way to go. And we'll look at an example and it'll help you understand it. It reduces variation among the subjects. And here's our promised example. Our example for matched pairs goes like this. I have to start taping during the day when I don't have these so much glare. Alright, the question that we're going to discuss are standing pulse rates higher than sitting pulse rates? My gut feeling is that the standing pulse rates are higher, but I'm not sure about that, so I'm going to do an experiment, and this is what we're going to do with it. There are 2 ways that we can do this, so you can see the difference between one that's a matched pair and one that's not. So the first one is we are completely going to randomize design. So that's what we were used to before today. We randomly decide which students in the class will sit and which students will stand. Then we measure their pulse rate for 1 minute, and we compare the sitting pulse rates to the standing pulse rates. So that is a completely randomized design. So it seems like it would be a good one. However, we know that just people in general have such variation in their pulse rates because of their height or their weight or their physical fitness or their amount of anxiety or whatever. So we have so many variations between people, we might not find conclusive results if we do it that way. So this is definitely a case where matched pairs would be the way to go. So let's look at what the design would look like using matched pairs. Each person receives both treatments in random order. So that's interesting. Each person. So how many people are in the matched pair? Actually, there's only one. So I'm going to go back there where I put that exclamation, not point, quotes around the 2. So we use 2 experimental units. And sometimes a matched pair is 1 experimental unit. So, and the difference is when you have 1 experimental unit, the person gets both treatments. First the one and then the other. So there's still a pairing that takes place. So up here we described it as 2 experimental units. One gets one treatment, one gets the other. Another form of matched pair is when there's 1 experimental unit or subject, and that subject gets both treatments. First one and then the other. So let's see how that will work. So this is our second design here. Each person receives both treatments in random order. So we flip a coin or we do some random assignment. So each person in the room will either sit or stand by random choice of flipping a coin or some other random process. So then they will take their pulse for 1 minute, and then if they were sitting, then they will stand, and if they were standing, then they will sit. And then they're going to compare the results of each person to their own number. So you're going to have each person standing and each person sitting. We won't be comparing each person to the next person, but only to himself. And this is called a matched pair because the block has 1 person who receives both treatments, and what is being blocked here during a matched pair, it blocks the variation in heart rate between individuals. So if we use the same individual sitting and standing, then we're blocking all the natural variation that we all have in heart rates. So let's look at some results of that and see what you think. My book minimizes all the pictures, but I'm going to shine it on there and see what you think. Here we have, in this picture here, I guess you have it in your book, it'd probably be easier to see, but I'll zoom in on this. Here we have some results about this experiment with the sitting and standing pulse rates. So, all right, hey, that's great. All right, so right now, except for the wiggling, we have sitting and standing. So here we have a whole class who was sitting, and here's their various pulse rates, and then we did the whole class standing. Notice there are some standings that were higher than sitting, but most of them showed a great amount of overlap. There's a lot of overlap. You can find lots of sitting pulse rates that are the same as standing pulse rates. So again, because there's so much variation in the individual heart rates, this is not surprising. So therefore, a better comparison would be doing each person against himself, sitting and standing. So that's what we did down here, and we actually did the difference. So we did standing minus sitting on this one. So if we get a positive number from standing minus sitting, then we know that the standing heart rate was higher. So you can see most of them were above 0. And here, these were 0, so that means the standing pulse rate was actually the same as sitting. And this one down here, I think somebody counted wrong, but nonetheless, that was the result. That means the sitting number, a pulse rate, was actually higher than the standing. So the difference between the two is often what's of interest when we're looking at a matched pair where this number of subjects is 1. Alright, so you can see how that gives us more information than this does. Okay, we'll finish with one last example of matched pairs and call it a day and call it a chapter. So, do nitrogen-filled tires hold air pressure better than air-filled tires? So regular atmospheric air is usually pumped into tires, but if we just put nitrogen, which is less likely to respond in flames, so it's flame retardant. So in an accident, nitrogen-filled tires are better, but we're just wondering if tires will hold their air pressure if they're filled with nitrogen compared to the normal air-filled tires. So we're going to do this with a matched pair design. We're going to go out and find about 31 different brands of tires, and we're going to compare. We're going to take one of those of each brand and fill it with air and one with nitrogen, and then we're going to take air pressure and we're going to set them outside for 1 year. Then we're going to look at the pressure in the air tire and the pressure in the nitrogen tire. And when we start, before the 1 year begins, we're going to make sure the pressure is identical in the air-filled tire and the nitrogen-filled tire. After 1 year, we're going to take each brand and take the air pressure in the air tire minus the pressure in the nitrogen-filled tire. And then we are going to see the results of that. So here is another matched pair. And we're going to look at the difference between the two. So here is air, as it says air minus nitrogen. So if the number is positive, that means the air number was higher after a year minus the nitrogen. So if you get a positive number, that means the air had the higher number and the nitrogen had the lower number. So we want to keep the air pressure in our tires. So here, air minus nitrogen means if you get a positive number, it means the air held more of the pressure. Oh, I'm sorry about that. That's not true. This is air minus nitrogen is I guess that is true. Let me think about that. I'll just read it. Since these data are paired by brand, we should look at the difference in pressure lost for each brand, air minus nitrogen. Here's a dot plot. Okay, so I was right. So they did a dot plot and they did a box whisker. We'll look at the dot plot, and here's the differences. So we can see that all these cases, air held more pressure than nitrogen. And over here, we can see that nitrogen held the pressure more than air. So the results are conclusive that the air did a better job. Alright, so with that in mind, we will recall that matched pairs are a good idea under certain scenarios for our design of our experiments. Matched pairs are a common form of blocking for comparing two treatments, and in some matched pairs each subject receives both treatments in a random order. In others, the subjects are matched in pairs as closely as possible, and each subject in a pair receives one of the treatments. So that kind of sums it all up for us. Alright, that brings us to the end of this section and almost the end of this chapter. We have one more day to go, and hopefully we will finish these videos before you go off to Thanksgiving break. If not, I will catch us up when I get back. Also, we will have a, if we finish 4.2 in this one more section, it's like a one-day section, 4.3, we'll have, oh, I know, we're finished section 4.2, so I can send home the quiz whatever day this ends up on, day 7. So expect Mr. DeBloom to hand you out a 4.2b quiz where you will study the information that we studied in section 4.2, which covers day 4, 5, 6, and 7, I believe. So you can verify that. And take that quiz and bring that back to me. If it happens to fall over the weekend here coming up, I guess that will be Thanksgiving break. Just please take that home and do it over the break. I'm hoping that it will be done before that. When we get back from break, and I'm there as well, we will review and test very soon when we get back. So hopefully you will let me challenge you to read over your notes 3 times. 3 times if you will do that for me over Thanksgiving break. I will give you a prize. So I can't tell you what it is because I haven't thought of it yet. But I will give you a prize if you can tell me you read over your notes 3 times during Thanksgiving break. All right, that's it. And there's one more day notes to come, one more video, and I'll see you then. Bye.